Hi everyone, Tolga here. It's my pleasure to introduce the first map synchronization algorithm implemented on a quantum computer. This work is in collaboration with Vlad and Christian from MPI, as well as Leo from Stanford, and marks the beginning of a series of works in quantum computer vision. We work on the problem of permutation synchronization. Many approaches in vision involve estimation of pairwise matches in isolation. This leads to noisy results that are inconsistent when a shape or image collection is considered. Our goal is to upgrade these matchings to be consistent among a given collection. Under bijective mapping, this multi-way matching can turn into a constraint satisfaction problem in which chaining permutations along cycles should yield identity. We call such cycles null cycles and essentially ask all cycles to be null. In the case of permutations, this can be expressed as an optimization over all the nodes that correspond to the canonical ordering of individual shapes or images. Here, the relative permutations are given, and the absolute ones are what we seek. Unfortunately, besides being non-convex, this problem is combinatorial and hence notoriously difficult to solve. The state-of-the-art algorithms try to work around this problem by relaxing permutations to continuous groups, suffering from some loss of accuracy. In this paper, we turn our attention into a completely different paradigm, quantum computation, and directly tackle the raw problem without relaxing thanks to the use of a quantum computer. Today, experimental yet practical quantum processing units are out. As opposed to classical computers, the adiabatic quantum computers, such as D-Wave, let the nature solve computational problems. To find optimal solutions, they first put qubits, quantum versions of bits, into their lowest energy state. Then, magnetic fields that represent the problem gently nudge this state towards the target energy landscape, a process known as quantum annealing. In this process, the quantum system is allowed to relax to an energy state that corresponds to the best configuration for solving the problem at hand. Unlike thermal annealers, this new annealer can overcome steep barriers by tunneling through them, making it possible to solve exponentially hard problems. Besides cancer diagnosis or protein analysis, AQC has already penetrated to our field, enhancing the prior art in non-max suppression, point-set alignment, or graph matching. Though we are the first ones to jointly process image collections and present evaluations on real data worthy of 15 minutes QPU time, a significant span in the quantum realm. The class of globally solvable optimization problems on D-Wave is known as quadratic unconstrained binary optimization problems, in short QUBO. Derived from the couplings and biases in Ising model, QUBO is composed of quadratic and linear terms minimized over binary variables. In order to map our problem to an AQC, we need to formulate it into a QUBO. In this work, QuantumSync, we do exactly that and show how to map the synchronization problem into a QUBO. We then embed this new problem into D-Wave and obtain the lowest energy solution after quantum annealing. We begin by expressing our problem as a vanilla QUBO, where the permutations are treated as general binary variables, and the symmetric coupling matrix fits the QUBO requirements. To ensure that the variables correspond to product of permutations, we take a close look at the space of permutations and formulate the permutationness as a linear constraint. Finally, we augment our vanilla QUBO with these constraints and show that this new formulation leads to another QUBO ready to be embedded into a quantum computer. Note, the sparsity in Q is beneficial for quantum computers. We solve small but real problems using the D-Wave API you see on the slide. Here, we match 4 key points across image pairs in the Willow dataset using AlexNet. We test our algorithm, as well as others, and observe that QuantumSync can match these well-engineered solutions, showing great potential for quantum machines. Check the paper for details. Quantum computation is still young, and there is a long way to go. We identify 2 main limitations. 1, the required number of qubits is exponential in the number of variables, and 2, the global optimality is likely but not guaranteed. We hope that the advances in physics will reflect positively to our field. Thank you for watching.